At first glance, European, American, and Swedish systems seem to compete on the same battlefield: power, efficiency, and performance. But that assumption is already a mistake. These systems were never built to answer the same questions, survive the same pressures, or tolerate the same risks. Each carries the hidden logic of the world that created it: its geography, its wars, its labor culture, and its tolerance for failure. When these systems collide in global projects, disasters, or conflicts, the result is rarely clarity. Instead, it produces controversy, blame, and unexpected breakdowns. What looks like superior engineering in one environment can become a liability in another. This is not a story about which system is best. It is about what happens when deeply different assumptions are forced to compete, and why the cost of that mistake is far higher than anyone expects. 3 worlds, 3 assumptions. Why these systems were never meant to compete. The clash between European, American, and Swedish systems is often framed as a simple comparison of quality or performance. In reality, these systems were never designed to compete on the same terms. They emerged from fundamentally different assumptions about geography, society, labor, and risk. When they are forced into direct comparison, the result is confusion, controversy, and frequent failure. Not because one system is inferior, but because each was built for a different world. The European approach grew out of constraint. After World War II from 1945 to 1949, much of continental Europe faced destroyed infrastructure, limited land, and dense population centers. Rebuilding required efficiency, coordination, and strict regulation. Countries such as Germany, France, and Italy developed systems optimized for compact environments, shared transport networks, and heavy state oversight. European design assumes rules will be followed, operators will be trained, and infrastructure will support the system. Compliance is not an obstacle, it is a design condition. This assumption shaped European industry through the second half of the 20th century. By the 1970s, environmental laws, labor protections, and safety standards became deeply embedded in engineering culture. Machines, vehicles, and industrial systems were designed to integrate seamlessly with regulation. Automation, interlocks, and fail-safe mechanisms became standard. The system protects itself and the user, even if that means stopping work entirely. In Europe, stopping is often preferable to risk. The American system developed under opposite pressures. The United States emerged from World War II with intact infrastructure, vast territory, and abundant natural resources. Expansion, not preservation, defined the post-war decades. From 1950 to 1980, American systems were built for scale. Distance mattered more than density. Speed mattered more than optimization. The assumption was simple: systems would be pushed hard, often beyond ideal conditions, and they needed to survive misuse. American design reflects this reality. Oversized components, mechanical simplicity, and tolerance for error became defining traits. Systems were expected to work far from centralized control, with limited supervision and improvised maintenance. Regulation existed, but it did not dominate design decisions until much later. In the American worldview, failure is acceptable if recovery is fast. The system exists to finish the job, not to preserve itself. Sweden represents a third, often misunderstood model. Swedish systems emerged from a small population, harsh climate, and strong social institutions. Unlike much of Europe, Sweden was not physically devastated during World War II, but it faced strategic isolation and resource constraints. From 1945 onward, Swedish industry focused on long-term sustainability, worker safety, and risk reduction. Companies such as Volvo, founded in 1927, and Scania, established in 1891, built systems around human survival rather than maximum output. The Swedish assumption is that people will make mistakes, and systems must absorb those mistakes without catastrophic consequences. This led to designs that emphasize redundancy, protective structures, and conservative performance limits. Swedish systems often appear slower or more cautious, but they are designed to minimize irreversible failure. Safety is not a feature, it is the core objective. Conflict arises when these assumptions collide. European systems struggle in environments where rules collapse, infrastructure is unreliable, or operators are undertrained. American systems face criticism in regulated, dense environments where emissions, noise, and safety margins matter more than raw output. Swedish systems are often seen as overcautious or inefficient in markets that prioritize speed and cost over long-term risk. These systems were not built to answer the same questions. Europe asks, how do we control risk? America asks, how do we push forward? Sweden asks, how do we survive failure? When one system is judged by another's priorities, it appears flawed. This mismatch becomes controversial in global projects from 1990 onward, when multinational procurement forced direct comparison. Buyers expected universal solutions. Engineers delivered context-specific designs. The result was disappointment, blame, and the false belief that one system had failed. The truth is simpler and more uncomfortable. These systems reflect the societies that built them. They encode national experiences with war, geography, labor, and risk. They were never meant to compete directly, only to function where their assumptions hold. Understanding this is essential, because the real danger is not choosing the wrong system. It is assuming that any system can work everywhere without consequence. Efficiency, scale, or safety. The first design conflict. The first and most fundamental conflict between European, American, and Swedish systems begins with a simple question. What matters most when everything cannot be optimized at once? Efficiency, scale, and safety all compete for priority, and no system can fully maximize all three. Each region chose a different answer based on its history, environment, and social expectations, and those choices continue to collide in the real world. European systems place efficiency at the center of design. After World War II, from 1945 to 1949, much of Europe had to rebuild quickly with limited space, fuel, and materials. Efficiency was not an abstract ideal, it was a survival requirement. Engineers were expected to extract maximum output from minimal input. This mindset shaped industries across Germany, France, and the Netherlands, where dense cities and shared infrastructure demanded machines and systems that were compact, quiet, and resource-conscious. Efficiency in the European sense is not just about fuel or energy. It includes space utilization, emissions control, labor coordination, and regulatory compliance. Machines are designed to fit within strict limits and to operate predictably inside complex systems. Automation and electronic controls enforce discipline. If conditions fall outside approved parameters, the system intervenes. Efficiency is preserved by preventing misuse, even if that means stopping work entirely. The American system answers the same problem with scale. The United States developed across vast territory with abundant resources and relatively low population density. From 1950 to 1980, growth was driven by expansion rather than constraint. Industries such as construction, mining, agriculture, and logistics prioritized volume and speed. The assumption was that inefficiency could be offset by size. Bigger machines, larger engines, and wider tolerances made it possible to move more material faster, even if costs were higher. Scale allows American systems to absorb inefficiency without immediate failure. Fuel consumption, noise, and emissions were historically treated as secondary concerns compared to output. Systems were built to work continuously under heavy load, often far from centralized oversight. Where European systems seek balance, American systems seek momentum. The risk is not wasted resources, but stalled progress. Swedish design introduces a third priority: safety. Sweden's industrial philosophy developed under very different pressures. With a small population, harsh climate, and strong labor protections, Sweden placed exceptional value on human life and long-term stability. From the mid-20th century onward, safety was embedded into system design rather than added later. Companies such as Volvo and Scania treated operator survival and accident mitigation as non-negotiable goals. Safety-focused systems often limit performance intentionally. Speed is controlled, power is moderated, redundancy is built in. These systems assume that accidents will happen and designed for survivability rather than prevention alone. Where European systems try to stop errors and American systems try to work through them, Swedish systems try to ensure that mistakes do not become fatal or irreversible. Conflict emerges when these priorities compete directly. Efficiency-driven systems can appear fragile under pressure. When automated controls intervene too aggressively, productivity collapses. Scale-driven systems can appear reckless, consuming resources and creating external costs that others must absorb. Safety-driven systems can seem slow or overly cautious in markets that reward speed and output. The controversy intensifies in international projects where a single solution is expected to satisfy all expectations. A European efficient system may fail in large-scale operations where flexibility is required. An American scaled system may be rejected in regulated environments where emissions and safety margins dominate. A Swedish safety-oriented system may lose bids because it prioritizes risk reduction over immediate cost savings. The core problem is that efficiency, scale, and safety are not neutral values. They reflect cultural decisions about acceptable risk. European systems assume that stopping work is preferable to uncontrolled operation. American systems assume that continued operation is preferable to delay. Swedish systems assume that no task justifies unacceptable harm. These assumptions become visible when systems are stressed. Under deadlines, efficiency collapses first. Under regulation, scale becomes a liability. Under crisis, safety determines survival. Each system excels when evaluated by its own priority and struggles when judged by another's. The first design conflict is therefore unavoidable. No system is wrong, but none is universal. Efficiency optimizes resources, scale conquers distance, and safety preserves life. Choosing one means accepting trade-offs with the others. Understanding this conflict is essential, because most failures blamed on engineering are actually failures of expectation. Systems break not because they are poorly designed, but because they are asked to solve problems they were never meant to address. When rules collide, regulation is a weapon or a limitation. Regulation is often presented as a neutral force, rules designed to ensure safety, fairness, and sustainability. In reality, regulation functions very differently across European, American, and Swedish systems, shaping not only how machines are built, but how power is exercised. When these systems collide globally, regulation stops being a background condition and becomes either a strategic weapon or a crippling limitation. In Europe, regulation is a foundational design driver. After World War II from 1945 to 1949, European governments rebuilt industry under strong state oversight. Scarcity of land, fuel, and capital demanded coordination rather than experimentation. By the 1960s and 1970s, regulations governing emissions, noise, worker safety, and transportation limits were deeply embedded in industrial planning. Engineers did not design first and adapt later. They designed within regulation from the start. This created systems that treat compliance as strength. European machines integrate sensors, interlocks, and automated controls to ensure legal operation at all times. If a limit is exceeded, the system intervenes immediately. From a regulatory perspective, this is success. Risk is controlled, liability is reduced, and standards are enforced consistently. In global markets, European manufacturers often leverage this compliance as a competitive advantage, especially in regions with strict environmental or safety laws. However, this same regulatory integration can become a limitation. When systems are deployed in environments where enforcement is weak, inconsistent, or irrelevant, regulation loses its protective value. Automated shutdowns and compliance-driven constraints can halt operations entirely. In regions facing instability, infrastructure damage, or emergency conditions, rules designed for peacetime efficiency become operational obstacles. The American relationship with regulation developed differently. For much of the 20th century, especially from 1950 to 1980, regulation lagged behind industrial expansion. The priority was growth. Systems were designed first, and rules were added later, often after problems emerged. This fostered a culture of flexibility. Compliance was something to manage, not something to embed deeply into core design. As a result, American systems often treat regulation as an external constraint rather than an internal control. Operators retain more discretion. Machines rely more on judgment than automation. When rules change or enforcement weakens, systems continue functioning with minimal modification. This adaptability becomes an advantage in volatile environments, but it also creates friction in regulated markets. From the 1990s onward, as global environmental and safety standards tightened, American systems increasingly faced barriers. Retrofitting compliance onto designs optimized for scale proved costly and complex. Regulation became a limitation rather than a tool. In some cases, compliance reduced performance without delivering the integrated efficiency seen in European systems, fueling criticism that American designs were outdated or resistant to change. Sweden occupies a unique regulatory position. Swedish regulation emphasizes prevention and social responsibility rather than enforcement alone. From the mid-20th century onward, rules were designed to align with industry rather than oppose it. Safety standards, labor protections, and environmental requirements were introduced gradually, allowing systems to evolve alongside regulation. This created strong trust between regulators and manufacturers. Swedish systems often exceed minimum regulatory requirements by default. Safety margins are conservative. Redundancy is expected. Compliance is not used as leverage against competitors but as a baseline assumption. This reduces conflict domestically, but creates challenges internationally. Swedish designs can appear over-regulated or unnecessarily constrained in markets that prioritize speed, cost, or output. Conflict emerges when these regulatory philosophies intersect in multinational projects. European systems arrive fully compliant but inflexible. American systems arrive flexible but face approval barriers. Swedish systems arrive safe but expensive. Regulation becomes a weapon when it excludes competitors and a limitation when it prevents adaptation. This was evident in infrastructure and industrial projects after 2000, where procurement rules favored compliance metrics over operational realities. Machines that met every regulatory requirement failed under real conditions, while non-compliant machines succeeded but faced legal or political backlash. Engineers were blamed for outcomes driven by policy decisions. Regulation also shifts responsibility. In European systems, failure is often attributed to misuse or non-compliance. In American systems, failure is attributed to conditions or execution. In Swedish systems, failure triggers systemic review rather than blame. These responses reflect deeper assumptions about control, risk, and accountability. The central controversy is not whether regulation is good or bad. It is whether regulation is treated as a design partner or an external constraint. When treated as a partner, systems become stable but rigid. When treated as a constraint, systems become flexible but exposed. When rules collide, no system escapes criticism. Compliance can prevent action. Flexibility can invite disaster. Overprotection can inflate cost. Under-regulation can magnify risk. Understanding regulation as a strategic force, not just a legal one, is essential. Because in global competition, rules do not simply limit behavior. They shape which systems survive, which fail, and which are even allowed to compete at all. Overbuilt, over-engineered, or overprotected, where each system breaks. When European, American, and Swedish systems are compared side by side, criticism often follows predictable lines. American designs are labeled overbuilt, European systems are accused of being over-engineered, and Swedish solutions are dismissed as overprotected. These labels are not entirely wrong, but they are incomplete. Each describes a failure point that emerges only when a system is pushed beyond the assumptions it was built on. Understanding where each system breaks reveals why none of them is universally superior. The American approach is frequently described as overbuilt. This reputation was earned through deliberate design choices. From 1950 to 1980, American industry expanded across vast territory with limited centralized control. Systems had to survive heavy loads, poor maintenance, and unpredictable operators. Engineers responded by increasing size, strength, and tolerance. Frames were thicker than necessary. Engines were understressed relative to their capacity, and mechanical systems favored durability over efficiency. This overbuilding delivers resilience. American systems often continue functioning despite visible damage. Components fail gradually rather than catastrophically. When something breaks, it is usually accessible and repairable. However, this resilience has a cost. Excess weight increases fuel consumption. Oversized systems create inefficiency that compounds over time. In regulated or resource-constrained environments, overbuilding becomes a liability rather than an advantage. What protects against failure also accelerates long-term cost. European systems are often described as over-engineered. This perception stems from a different set of pressures. After World War II, from 1945 to 1949, Europe rebuilt under severe constraints. Space, fuel, and materials were limited. Engineering excellence focused on optimization rather than excess. Systems were designed to achieve maximum performance within strict boundaries. Tight tolerances, integrated electronics, and automated controls became defining features. Over-engineering, in this context, is not extravagance. It is precision. European systems excel when conditions are controlled. They deliver high efficiency, low emissions, and predictable performance. But this precision creates fragility. Interdependent systems leave little room for error. A failure in one component can disable the entire system. When operating environments become chaotic, complex systems can break suddenly and completely. This fragility becomes visible in regions with poor infrastructure or inconsistent maintenance. European systems may shut down to protect themselves, preserving internal integrity while halting external progress. From an engineering standpoint, this is logical. From an operational standpoint, it is disruptive. Over-engineering protects the machine but can sacrifice the mission. Swedish systems are often criticized as overprotected. This criticism reflects Sweden's unique priorities. With a small population, harsh climate, and strong social safety culture, Swedish design places exceptional emphasis on human protection and long-term stability. From the mid-20th century onward, companies such as Volvo and Scania embedded safety deeply into system architecture. Redundancy, controlled performance limits, and protective structures are not optional add-ons. They are core design principles. Overprotection minimizes catastrophic outcomes. Swedish systems are designed to absorb mistakes, reduce injury, and limit irreversible damage. However, this safety-first approach can reduce speed, flexibility, and cost competitiveness. In markets that reward rapid output or low upfront cost, Swedish systems may appear slow or inefficient. Overprotection becomes a weakness when survival is less critical than speed. The breaking point for each system emerges under different pressures. American systems break economically. They survive physically but accumulate hidden costs through fuel consumption, wear, and inefficiency. European systems break operationally. They preserve internal health but stop functioning when external conditions fall outside design limits. Swedish systems break commercially. They perform safely and reliably, but struggle to compete in environments that undervalue risk reduction. These breakdowns are often misinterpreted as engineering failure. In reality, they are failures of context. Systems perform exactly as designed, but in the wrong environment. Overbuilding assumes resources are available. Over-engineering assumes control is maintained. Overprotection assumes safety is the highest priority. Global projects expose these assumptions brutally. From 1990 onward, multinational procurement forced direct comparison between systems built for different realities. Buyers expected universal solutions. Engineers delivered specialized ones. When systems broke, blame followed. American designs were called wasteful. European designs were called fragile. Swedish designs were called impractical. The deeper problem lies in expectation. No system can maximize strength, efficiency, and safety simultaneously. Trade-offs are unavoidable. When a system's strength is pushed too far, it becomes its weakness. Overbuilding strains resources. Over-engineering collapses under chaos. Overprotection limits adaptability. Where each system breaks is therefore predictable. It breaks where its core assumption fails. The mistake is not in the design, but in the belief that design choices can escape context. This exposes a critical truth. Engineering does not fail randomly. It fails precisely where it was never meant to succeed. Maintenance reality. Check. Who survives when support disappears? Maintenance is where engineering theory meets operational reality. Machines are rarely judged by how they perform when support is available. Spare parts are stocked, and technicians are on call. They are judged when support disappears. When logistics fail, schedules collapse, and problems must be solved immediately or not at all. In those moments, the differences between European, American, and Swedish systems become impossible to ignore. European systems are designed with the assumption that support exists. This assumption is historical. After World War II from 1945 to 1949, much of Europe rebuilt industry alongside infrastructure, regulation, and service networks. Maintenance became a planned process rather than an emergency response. Machines were integrated into ecosystems of dealers, certified technicians, and scheduled servicing. When used as intended, this model delivers reliability and long service life. The weakness appears when that ecosystem breaks down. European machines often rely on specialized diagnostics, proprietary software, and manufacturer-approved parts. A failure that is minor mechanically can become critical operationally if it triggers a system lockout or automated shutdown. Without authorized tools or technicians, a machine may remain idle despite being physically intact. In unreliable supply chains, downtime becomes the dominant cost. American systems approach maintenance from the opposite direction. They are built with the expectation that support may be delayed, incomplete, or improvised. This mindset developed as American industry expanded across remote regions where service infrastructure lagged behind deployment. From 1950 to 1980, machines were expected to be maintained by general mechanics using basic tools. Simplicity was not a limitation. It was a survival strategy. As a result, American systems tend to degrade rather than stop. Leaks, vibration, overheating, and partial failures are tolerated. Components are accessible, interchangeable, and forgiving. Maintenance is continuous and imperfect, but work continues. When support disappears, these systems survive by sacrificing efficiency and long-term health for short-term functionality. This does not make American maintenance cheap. Costs accumulate through higher fuel use, accelerated wear, and frequent minor repairs. However, these costs are predictable and spread over time. For many operators, predictability is preferable to sudden, total downtime. A machine that runs poorly but runs is often more valuable than one that is perfect but inactive. Swedish systems occupy a middle position shaped by different priorities. Maintenance philosophy is tied closely to safety and risk reduction. Systems are designed to prevent dangerous operation even if that limits functionality. Redundancy and protective mechanisms reduce catastrophic failure, but restrict improvisation. Procedures are conservative, prioritizing human safety over continuity of operation. When support disappears, Swedish systems tend to fail safely. They may limit performance or shut down before damage or injury occurs. This protects operators and preserves equipment, but it can halt progress entirely. In stable environments, this is acceptable. In time-critical situations, it can be a serious disadvantage. The difference becomes stark in remote projects, disaster response, and post-conflict environments. Support infrastructure is often damaged or non-existent. Parts may take weeks to arrive. Skilled technicians may be unavailable. In these conditions, maintenance philosophy determines survival more than design quality. European systems struggle when diagnostics and authorization are required to resume operation. American systems continue through improvisation. Swedish systems prioritize safety even if that means stopping. None of these outcomes are accidental. They reflect assumptions about what happens when things go wrong. Global supply chain disruptions around 2020 made this reality visible even in developed markets. Operators accustomed to rapid support faced delays. Complex systems experienced extended downtime. Simpler systems remained operational through adaptation. Maintenance shifted from a background function to a strategic concern. Training also plays a critical role. European and Swedish systems assume disciplined operators who follow procedures closely. Improper maintenance increases failure risk. American systems assume variability in skill and behavior. They tolerate mistakes but pay for that tolerance over time. The central question is not which system is easier to maintain, but which survives when maintenance cannot be performed correctly. Survival under maintenance stress does not mean optimal performance. It means continuity. In the real world, support always disappears eventually through conflict, disaster, budget cuts, or logistical failure. When that happens, machines reveal their true priorities. Some protect themselves, some protect people, some protect the mission. The maintenance reality check is unforgiving. It does not reward elegance or efficiency. It rewards survivability under neglect. And in that test, the question is not which system is best, but which one keeps going when everything else stops. Human error versus system control. Who blames the operator? When machines fail, responsibility is rarely neutral. Someone is blamed, and in most cases, that blame falls on the operator. How European, American, and Swedish systems assign responsibility reveals a deep divide in design philosophy, one that shapes machine behavior under stress, accident investigations, and how failure itself is defined. European systems are built around control. Human error is treated as a predictable risk that must be minimized through design rather than managed through judgment. This mindset intensified after World War II from 1945 to 1949, when European industries rebuilt under strict regulation and low tolerance for accidents. Dense populations, shared infrastructure, and strong labor protections meant a single mistake could carry serious social and legal consequences. Engineering responded by reducing discretion. In European design, systems do not trust the operator by default. Sensors, interlocks, automated overrides, and compliance checks exist to prevent incorrect actions before damage occurs. If an operator exceeds defined limits, the system intervenes. If unsafe conditions persist, the machine shuts down. Responsibility shifts away from human judgment and into system logic. When failure occurs, it is often recorded as misuse or procedural deviation rather than a design flaw. This approach reduces accidents and improves predictability, especially in regulated environments. However, it comes at the cost of flexibility. Operators are expected to follow procedures exactly. Deviations are treated as faults, even when conditions demand improvisation. In unstable or rapidly changing environments, control systems designed to prevent error can become barriers to action. American systems approach the problem differently. Human error is assumed, not prevented. From 1950 to 1980, American machines were deployed across vast territories with inconsistent training, long shifts, and harsh working conditions. Engineers understood that operators would improvise, push limits, and make mistakes. Instead of blocking those behaviors, systems were designed to tolerate them. In this model, control is minimal, and authority remains with the operator. Machines respond to input even when it is imperfect. Failure is treated as part of normal operation rather than a violation of rules. When something breaks, responsibility is shared between conditions, equipment limits, and human judgment. Systems allow consequences to accumulate gradually instead of shutting down immediately. This tolerance creates resilience. Operators can adapt to unexpected situations and continue working when conditions change. But it also increases risk. Accidents may be more severe, and damage may go unnoticed until it becomes critical. When failure finally occurs, blame becomes diffuse. It is often unclear whether the operator pushed too far or the system allowed too much. Swedish systems represent a third position. They assume that human error is inevitable, but unacceptable if it leads to serious harm. From the mid-20th century onward, Swedish design focused on minimizing the consequences of mistakes rather than eliminating mistakes themselves. Safety is embedded into system architecture rather than added later. Swedish machines intervene not to enforce discipline, but to protect people. Controls may limit speed, force, or access to hazardous functions. If unsafe behavior continues, systems reduce capability before shutting down completely. The goal is to preserve life and prevent irreversible damage while maintaining limited operation. Responsibility is shared explicitly between system design and human behavior. This approach has reduced fatalities and severe injuries, but it can frustrate operators accustomed to autonomy. Machines may feel restrictive or slow. Decisions are guided rather than commanded. In environments that prioritize speed, output, or cost reduction, this is often perceived as inefficiency. Conflict emerges when these systems are deployed globally. European systems often assign blame to operators who deviate from procedure. American systems attribute failure to circumstances or operational pressure. Swedish systems trigger broader review of system design rather than isolating individual fault. These responses reflect deeper cultural attitudes toward responsibility and risk. The controversy becomes visible in incident reports and accident investigations. European documentation focuses on compliance and deviation. American reports emphasize context and judgment calls. Swedish investigations look for systemic contributors and long-term prevention. None of these approaches are neutral. Each shapes how operators behave in the future. Under pressure, the differences intensify. In emergencies, operators may attempt to override safeguards. European systems resist overrides and enforce shutdowns. American systems allow continued operation at increased risk. Swedish systems limit damage while prioritizing human safety. Outcomes depend on whether speed, control, or protection is valued most. No approach eliminates error. European control reduces mistakes but limits adaptability. American tolerance increases adaptability but accepts damage. Swedish protection minimizes harm but constrains output. Operators will always make mistakes. The real question is whether systems are designed to punish those mistakes, absorb them, or protect against their consequences. That choice determines not only how machines fail, but who is held responsible when they do. Crisis, conflict, and harsh terrain. Which approach fails first? Crisis strips systems of their assumptions. Conflict removes support. Harsh terrain punishes every design shortcut. When European, American, and Swedish systems are pushed into these environments, performance is no longer measured by efficiency ratings or certifications. It is measured by survival, continuity, and whether machines can function when conditions collapse. The real question is not which system looks best on paper, but which one fails first when reality turns hostile. European systems are often the first to struggle in crisis environments. Their strength, precision, and control depends on stability. Regulations, calibrated inputs, trained operators, and predictable maintenance are assumed. In conflict zones or disaster areas, those assumptions collapse quickly. Infrastructure is damaged, fuel quality becomes unreliable, and operators may lack specialized training. Under these conditions, tightly integrated systems become fragile. European machines are designed to protect themselves. Sensors detect abnormal conditions, and automated safeguards intervene. When limits are exceeded, systems reduce output or shut down entirely. From an engineering perspective, this prevents catastrophic damage. From an operational perspective, it can be fatal to the mission. In crisis scenarios, stopping work can be worse than damaging equipment. European systems often fail not because they break mechanically, but because they refuse to operate outside defined parameters. American systems respond differently. They are built for environments where control is limited and conditions are unpredictable. This philosophy developed through decades of operating in remote regions, large infrastructure projects, and military logistics. From 1950 to 1980, American equipment was expected to function far from supply chains and service centers. Durability and tolerance mattered more than optimization. In harsh terrain, American systems often keep going long after efficiency collapses. Engines run hotter, components wear faster, and leaks or vibration are accepted. Failure is gradual rather than immediate. This allows continued operation under pressure, which is critical in emergencies, combat support, or disaster response. However, this resilience comes at a cost. Damage accumulates quietly, and long-term reliability declines. In prolonged crises, American systems often fail through exhaustion. What survives the first phase of conflict may collapse later due to accumulated wear, fuel strain, or neglected maintenance. They do not fail cleanly. They fail loudly, expensively, and sometimes catastrophically. The advantage is time. The disadvantage is sustainability. Swedish systems occupy a more balanced but complex position. They are designed with crisis in mind, but not conflict in the same sense. Swedish design emphasizes human survival, redundancy, and controlled degradation. Harsh terrain and severe weather were always part of the design equation. Safety structures, conservative performance limits, and robust frames allow machines to protect operators even as conditions deteriorate. In crisis environments, Swedish systems often continue operating longer than European ones because they tolerate deviation without immediate shutdown. However, they are more restrictive than American systems. Performance is deliberately limited. Speed and output are reduced to maintain safety margins. In fast-moving conflict or emergency response, this caution can slow progress. Swedish systems tend to fail strategically rather than mechanically. They prioritize preventing irreversible outcomes, even if that means sacrificing momentum. In environments where speed determines success, this becomes a disadvantage. In environments where survival and recovery matter more than completion, it becomes a strength. Terrain magnifies these differences. Urban rubble, deserts, mountains, and frozen ground expose design assumptions. European machines struggle with vibration, dust, and uneven surfaces that disrupt sensors and control systems. American machines absorb these stresses through mass and tolerance. Swedish machines manage them through controlled operation and structural protection. Conflict environments further distort priorities. Rules disappear. Compliance becomes irrelevant. What matters is whether the machine works now. European systems, built to obey rules, often fail when rules no longer exist. American systems, built to ignore rules, thrive initially, but consume resources rapidly. Swedish systems attempt to preserve life and equipment, even if progress slows. Historical patterns reinforce this divide. During military and humanitarian operations from 2003 onward, American-built equipment dominated early phases due to repairability and tolerance for abuse. European systems proved more effective during stabilization and reconstruction, once infrastructure and maintenance returned. Swedish systems performed best in hazardous support roles where operator safety was critical. Which approach fails first depends on how failure is defined. European systems fail operationally first. They stop working. American systems fail structurally later. They wear out. Swedish systems fail competitively. They lose speed and output. None of these outcomes reflect poor engineering. They reflect different priorities under stress. Crisis exposes what systems are designed to protect: rules, progress, or people. Crisis, conflict, and harsh terrain do not reward perfection. They reward alignment between design and reality. The system that fails first is not the weakest. It is the one farthest from the environment it was built to survive. The hidden cost of choosing the wrong system and why it matters. Choosing the wrong system rarely looks like a mistake at the start. On paper, specifications are impressive, compliance boxes are checked, and procurement decisions appear justified. The real cost only emerges later, quietly, gradually, and often irreversibly. In global projects, disasters, and conflicts, the mismatch between system design and operating reality creates hidden costs that far outweigh purchase price, fuel efficiency, or headline performance. The first hidden cost is downtime. When a system is deployed outside the environment it was designed for, failure does not always arrive as a dramatic breakdown. More often, it appears as repeated stoppages, restricted operation, or prolonged inactivity while waiting for parts, authorization, or expertise. A machine that shuts down to protect itself may be technically intact, but operationally useless. Crews wait, schedules slip, entire projects stall. Downtime multiplies costs far beyond the machine itself. The second cost is logistical strain. Systems optimized for precision often depend on specialized supply chains, proprietary components, and certified technicians. When infrastructure is weak or disrupted, maintaining those chains becomes expensive or impossible. Transporting parts, flying in specialists, or halting work until approval is granted adds layers of cost that were never included in the original budget. What looked efficient in a controlled environment becomes fragile when logistics fail. The third cost is resource consumption. Systems built for tolerance and durability often survive harsh conditions, but they do so by consuming more fuel, more consumables, and more maintenance hours over time. These costs are incremental and easy to overlook. Fuel bills rise slowly. Wear accumulates quietly. By the time the full cost is visible, it is already sunk. The system worked, but at a price that eroded long-term viability. Human cost is another factor rarely calculated. Operators forced to work around restrictive systems experience frustration and reduced effectiveness. Operators pushed to keep tolerant systems running under degrading conditions face fatigue and increased risk. In both cases, morale drops, errors increase, and turnover rises. Training costs grow as new operators struggle to adapt to systems that do not match their environment or experience. There is also a strategic cost. Choosing the wrong system locks organizations into patterns that are difficult to reverse. Maintenance contracts, spare parts inventories, and operator training create dependency. Switching systems mid-project is often impossible without massive disruption. Early procurement decisions shape outcomes years later, long after the decision-makers have moved on. This mismatch became especially visible in multinational operations from 2000 onward, where equipment designed for one regulatory, geographic, or cultural context was deployed globally. Machines praised in one region underperformed in another, not because they were poorly built, but because they were misused. The cost was measured not only in money, but in delayed recovery, failed objectives, and damaged credibility. The wrong system also distorts accountability. When failure occurs, blame shifts. Operators are accused of misuse. Engineers are accused of over-design or under-design. Manufacturers are accused of complexity or inefficiency. In reality, the failure lies in expectation. The system did exactly what it was designed to do, just not what the situation required. Another hidden cost is opportunity. While organizations struggle to keep mismatched systems operational, competitors using better aligned equipment move faster, adapt sooner, and recover quicker. Projects are lost not because of inferior capability, but because of slower response. In crisis environments, speed of adaptation often matters more than raw performance. Environmental and political costs also emerge. Systems that consume excessive resources or fail to meet local expectations attract scrutiny. Public backlash, regulatory penalties, or loss of trust can follow. What begins as a technical decision becomes a political liability. Why this matters is simple. Systems are not neutral tools. They embody assumptions about rules, people, and conditions. When those assumptions hold, performance is impressive. When they do not, failure is expensive. The hidden cost is not paid up front. It is paid over time, under pressure, when change is hardest. The lesson is not to choose the most advanced, the most durable, or the safest system in isolation. It is to choose the system whose assumptions most closely match reality. That requires honest assessment of terrain, support, training, risk tolerance, and time pressure. Ignoring those factors guarantees cost overruns, delays, and failure. In the end, the most expensive system is not the one with the highest price tag. It is the one that cannot adapt when conditions change. Choosing the wrong system does not just waste money. It wastes time, effort, and opportunity. And in critical environments, those losses matter far more than any specification sheet ever will.